Okay. So design club today at 3:30 in S1324. So if you can make it, do it. And if not, send me an email and I'll tell you what we talked about. And yeah, we're just sort of trying to get, like, some people are starting to get things going to the point of like thinking how we're going to do stuff, get software installed that we need, and get materials. And so we're just starting to get stuff going. It's going to be fun.
Some projects.
Yes, exactly. All right, so in thermodynamics, we've been talking about, well, we've been using the first law. And we've been doing that for fixed amounts of material. And so, and then last time we talked about simple compressible materials. Along the lines of simple compressible materials, today we're going to talk about two simplified models for doing calculations. The first one is treating a material as incompressible. That's useful for liquids, not usually useful for gases. And then second, the ideal gas model. And this is useful for gases. So we're going to talk about those today. Before we do that, I'm going to introduce enthalpy. And C sub P and C sub V, these are the specific heats. And I'm going to do that first because those are going to come up when we talk about these simplified models. But enthalpy is not going to really be useful to us until we go from these fixed amounts of material that we're looking at to control volumes. So I don't think we're going to get to this today, but we'll use enthalpy when we talk about the first law for control volumes. So that's sort of supposed to, it's a little messy, but it's supposed to explain how this stuff we're going to talk about all kind of fits together. We're going to talk about enthalpy and these specific heats. Enthalpy is, we're bringing it up because it's going to be useful when we talk about first law for control volumes. And control volumes is like if you have a turbine or a nozzle or something, and you have material flowing in one side and flowing out the other side. You can't track the material as it comes in, it would take way too much analysis, and you can't track it going out. You can track that volume, and so you have to change the math in order to be tracking a volume and not tracking specific particles, specific material. And then we're going to talk about enthalpy and the specific heats when we talk about these simplified models. Okay, so first I'm going to introduce enthalpy. It's capital H. And the specific heats, C sub V and C sub P. Enthalpy is a property. It's an extensive property, but you can also calculate it per mass. And the intensive enthalpy per mass is in tables. So if you have tables for a material, you can look it up. And the first calculation we'll use some values from a table to calculate it. And then you could look up the corresponding enthalpy in the table, and you'd see that it's not an approximation. It's just using the definition. It's exactly what it is in the table.
Wait, so the intensive version of enthalpy, that's going to be enthalpy per what unit then?
Per kilogram mass.
Okay,
yeah.
Yeah, so per mass depending on the material.
That's right.
Gotcha.
Okay, so you mentioned this before. You can sort of roughly think of enthalpy as the internal energy plus the work required to put the material into the volume that it occupies. Let's say the work required to make space for it. I've never found that particularly useful to think of it that way, but I tend to just think of it as an artifact of a calculation that we'll see when we talk about control volumes. It's a cross term that arises in the derivation of the first law for control volumes. And since it comes up a lot, it's easier to just look up one value than to look up 3 values and calculate it. It's an extensive property with units of energy. And tables give the intensive lowercase h, which is enthalpy per mass. Okay, so let's just do a calculation of the enthalpy. So these are values that I just got out of the table. So let's say that we have 2 kilograms of liquid water at saturation, at 1 bar of pressure. Calculate the extensive enthalpy from the tables using, we're going to look up values of the specific internal energy, the pressure, and the specific volume. All right, well, this is at saturation, which means that, so if you're not at saturation, if you're away from the saturation temperature and pressure, then you need 2 properties to look up any other properties. But at saturation, 1 is enough. So all we need is the pressure if we know that it's at saturation. And so this is, yep.
And again, saturation just means any more energy, it starts turning into vapor.
Yeah, or if it's saturated vapor, any less energy and it starts turning into liquid.
Yeah, that's just something on that curve.
It's in the phase change state. So if it's all saturated liquid, then it's all liquid ready to change. If it's vapor, then it's all vapor ready to change to liquid if you take away energy. And anywhere in between, then you have to deal with the quality, that, remember that variable X, and you have to do that in the calculations. Yeah. All right, so in the table, we use the pressure table. And in the fluid column, because this is a liquid, you get that the specific volume is 1.0432 times 10 to the minus third meters cubed per kilogram. And look up the pressure. 1 bar is 1 times 10 to the 5th pascals. The specific internal energy for the liquid, for the fluid, is 417.36 times 10 to the 3rd joules per kilogram. You always have to be careful when you use the tables. They don't use SI units. Usually they're using kilojoules or something funky, so be careful with your units. I just always put it into SI units because then I know I can just multiply and divide numbers and not worry about it.
Keep a track of whether or not there's a kilo in front.
Yeah, yeah. Okay, so now we're going to use these to calculate the intensive enthalpy. So the intensive enthalpy, I said up here, is the extensive enthalpy per mass. Let me write that down here. The intensive is, so if you divide both of these 2 terms by the mass, you get the specific internal energy. And now divide the pressure times volume by the mass. The pressure, there's no such thing as pressure per mass. Pressure is already intensive. So just divide the, think of dividing the volume by the mass, and you just get the pressure times the specific volume. So that's the intensive enthalpy. And so that's what you can calculate from the table values. So H here is 417.36 times 10 to the 3rd plus 1 times 10 to the 5th times 1.0432 times 10 to the minus third, and you get 834.92 times 10 to the third joules. So we were sort of acting like our table didn't have a column for enthalpy. I suppose it's possible you'd find some that didn't. But then if you just look over at the right entry in the enthalpy column for intensive enthalpy, it would give you exactly this value because that's just a definitional thing. We didn't want the intensive enthalpy, we wanted the extensive. So now you just have to multiply it by the mass.
Units of that lowercase h are joules per kilogram?
Yes, thank you. So 2 times 834.92 times 10 to the third, and you get what? Oh, I'm sorry. I gave you the wrong one here. That's just not what that comes out to if you calculate it. This comes out to 417.46 and that's times 10 to the third. And so multiply it by 2 kilograms, and you get.
Second terminal for the intensive one.
Mm-hmm.
Don't you have an e to the 5 and then an e to the negative third, which means e to the 2? So wouldn't that change that from like 417 plus? Wouldn't that be 104 point something?
This one is, the 417 is times 10 to the third. This is, well, yeah, so times 10 to the second. So, but this is like 4.17 times 10 to the fifth, right? Because it's 417 something.
Oh, yeah.
So yeah, it doesn't change it very much.
Yeah, okay, I was just looking at my decimal places.
Yeah. So 834.92 times 10 to the third joules. In any material, any state, that's the definition of enthalpy. So now the specific heats. There are 2 of these, and these are going to come up as one of the reasons that it's useful to have those simplified models that we're going to talk about next. So the first one is C sub V, the constant volume specific heat. That is the partial of the intensive internal energy with respect to temperature, calculated at a constant volume. And then C sub P, the constant pressure specific heat, is the partial of the intensive enthalpy with respect to temperature, calculated at constant pressure. These feel like sort of random collections of letters, but they will come up later. But it's going to be useful to remember these, so it's very likely that I'll ask you these on a quiz.
Wait, why is one with, oh, okay, never mind. I just realized now I'm looking at enthalpy. If
Okay.
you hold P constant, then that second term doesn't come into play. Or I should say hold V constant. So I'm just looking at why one's with respect to U, one's with respect to H.
Just because it's going to end up being useful later in calculations. That's the only reason. We don't have any way to know yet why anyone came up with these ugly things.
Gotcha. I just trying to remember. I think the first time I learned more than this, I think it was heat with respect to temperature, not energy.
Oh.
Not important.
Right. Well, we'll see examples that kind of bring out why in special cases that would be,
why would
it would be the same thing.
Energy or enthalpy?
Yeah.
Okay.
Okay, so for now, there's no reason for, C sub P and C sub V, but we'll see why later. Okay, so now you don't always have tables for any material or mixture you want. So yeah, you don't always have tables for the material or mixture that's desired. So often you need other ways to calculate properties, some properties from a set of other properties that you know. So often you need other equations of state. To calculate properties at a state. So I'm going to bring up two simplified models. The first is incompressible. And that's useful for liquids. And the second is ideal gas, the ideal gas assumption, and that's useful for gases. And so in cases where you don't have the property tables, these can often do the same things for you, or a lot of the same things. So I'll start with the incompressible assumption. It's mostly useful for liquids. It can sometimes be useful for solids too. This, for the most part, isn't a class about solids. Most of the useful stuff for engineering happens between liquids and gases. So what we're going to assume is that the specific volume is a constant. And that's something you're going to look up at a desired temperature, because it does, the specific volume of a liquid does vary. It just doesn't vary with temperature very fast. So you want to make sure that you get this value for the right range of temperatures. But once you're in that right range, you can assume that it's constant. Okay. And then we're going to assume that the specific internal energy is just a function of temperature. It isn't affected by anything except temperature. Okay, so that's the starting assumption. And as a consequence of these, we'll see that CV is equal to CP, and it's equal to the total derivative of the specific internal energy with respect to temperature, and we're just going to call that C, since they're the same. And this is what you call the specific heat. If any of you in Physics 1 talked about specific heat, you probably did it with just this single value. Okay, so to make sense out of this, so why is this the case? Well, CV is the partial of lowercase u with respect to temperature held at constant volume. But U doesn't vary with anything except temperature. That's one of the two definitions of this model. And so this immediately just becomes dUd temperature. And this is just because U is U of temperature. Cp is the partial of lowercase h with respect to T at a constant pressure. And so if you use the definition of specific enthalpy, that's the partial with respect to temperature of the specific internal energy plus P times specific volume, all done at a constant pressure. Well, since it's a constant pressure, so the pressure isn't changing, and the specific volume doesn't change because that's one of our assumptions, and U is only a function of T. So we can write this as the partial of U with respect to T for a constant pressure plus the partial of PV with respect to temperature at a constant pressure. This term goes away, and you just get the same thing again, derivative of the specific internal energy with respect to temperature. So the main use of this is it lets us calculate changes in internal energy. Based only on the temperature. You know, using only the change in temperature. And so in physics 1, if you did any kind of thermal stuff, you definitely did this calculation for liquids and solids. So let's do an example and see how it works. So let's say that you have 2 kilograms of liquid water that goes from 320 Kelvin to 324 Kelvin. As pressure goes from 101 times 10 to the third pascals to 140 times 10 to the third pascals. We're going to assume that the specific heat is 4.18 kilojoules per kilogram times Kelvin. And we want to calculate the change in internal energy and the change in enthalpy. So that specific heat, that's something you can look up in a lot of tables. One of the tables that's given in D2L says something like complete property tables, I think, and on like the second page of stuff, you can look up the specific heat of water over a range of, I think, about 100 degrees Celsius, you know, basically between boiling and freezing at a usual room temperature. And in this problem, I put in something that's totally irrelevant, but that's something you're going to have to get used to with problems in this class.
Yeah, I did that a lot.
Yeah, you know, I don't tend to do that myself, but a lot of the problems that are given are from the textbook, and they seem to like to do that. I mean, I can understand the benefit of it.
A lot too, where you're taking a lot of measurements. And
Yeah,
not necessarily
exactly.
relevant information.
I'm sure that's why they do it. Yeah. So, anyways, the pressure, the whole point of this, the whole thing to notice is if you have an incompressible material, and we're treating liquid water as an incompressible material, then the only thing you need in order to calculate the internal energy is the change in temperature.
Yeah, because it doesn't matter if there's a change in pressure with our partial just because there's no change in volume.
Right.
So it's still zero for our partial derivative.
That's right.
Okay.
That's right. I mean, I guess, yeah, really, that C sub P holds the pressure constant anyways. So,
right?
All right, so what we have is we're going to use this definition for incompressible materials that says C is equal to du dt. And so since we're assuming this is constant, we can think of this as du is equal to c dt and integrate both sides. And we can think of both of these integrals as happening from state 1 to state 2. And so if we integrate du, we get the change in specific internal energy. C is 4.18. I guess I'm doing this in, let's change it to SI units. I just said that I tend to do that. So let's change this to 4.18 times 10 to the third. So now we're in joules per kilogram Kelvin. The temperature, as the temperature goes from 320 to 324. And so you get 4.18 times 10 to the third times 324 minus 320 is 4. And you get 16.72 times 10 to the third. This is in joules per kilogram. We want the actual change in internal energy, not the specific. So we have to multiply this by the mass, and we have 2 kilograms. And so we get 33.44 times 10 to the third joules. So if you're dealing with a liquid without like enormous changes in temperature, keep in mind that you can pretty much always calculate the change in internal energy based on just what you know about the temperature. Now we want to calculate the enthalpy. So I'll do that for specific enthalpy again. So the change in specific enthalpy is equal to the change in specific internal energy plus the change in PV. We're assuming that the specific volume is constant. So this is the change in specific internal energy plus V times the change in, oh, look at, we do need this. I was too hasty. So we didn't need it for the internal energy. I'm going to erase this, and if you don't watch the video, you'll never know that I was wrong about that. And so for the change in specific internal energy, you get 16.72 times 10 to the third. And then plus, did I give a, I guess I didn't give a specific volume. That stays pretty constant for any liquid. For water, that tends to be around Well, you know, the density is about 1,000 kilograms per cubic meter. So it's going to be about 0.001 cubic meter per kilogram. And then we're going to multiply that by the change in pressure, which is 39 times 10 to the third pascals. And so you get a change in specific enthalpy of 55.72 times 10 to the third joules per kilogram. That's the specific change in enthalpy. We want the actual change in enthalpy, so we multiply that by 2 kilograms. So 111.44 times 10 to the third, and this is in joules.
A quick question.
Yeah.
For enthalpy in our PV term, I thought by definition it explicitly was referring to like the work term by expansion, where our gas isn't expanding.
Oh,
So, but it doesn't in this case.
right. It's so that sort of intuitive meaning of it is like how much energy it would take if you didn't have that material there, you had everything else living there, and then that material nudged its way in to the space that it occupies.
Oh, to make that right.
Yeah.
Oh, okay.
So it's the expansion that it would take if you start by assuming it's not there.
Yep, and then just stuff a bunch in.
Exactly.
That pressure.
Exactly. Right.
Oh.
So that's the expansion it's talking about, like a fake expansion, you know.
Yeah.
Okay, so notice. For an incompressible material, given the value for C and the change in temperature, you can calculate the change in specific internal energy. Two, given C and the specific volume, and changes in temperature and pressure, you can calculate the change in specific enthalpy. Any questions about that incompressible model? So I think it's useful just anytime you see a problem where you're dealing with a liquid, keep that in the back of your mind that you can do these calculations, okay? We're dealing with gas more often than we're dealing with liquids, and things get more complicated, but if you're dealing with a liquid, this is always something that's an option.
Yeah, because given something compressible like a gas, we're then going to have to use a state function like ideal gas law to then like rewrite pressure.
Yeah,
volume, and then
right. Yeah, it all gets a lot more complicated. But so now I'm going to talk about the ideal gas law and talk about the assumptions that go along with that and what you know if you have an ideal gas. Okay, so this first one was the incompressible assumption. So now we're going to talk about the ideal gas assumption. And it's all based on this one amazing fact. This fact is amazing. For any gas without super high pressure, and without a super low temperature, the pressure times the molar specific volume divided by the temperature. Okay, so this, remember that overbar always means a specific value per mole. So this is the volume divided by the number of moles. This is no matter what gas you're talking about, what temperature and what pressure, as long as they're not too extreme. This comes out to be the same value. That's amazing. And this is the universal gas constant. It's 8.314 kilojoules per kilomole times Kelvin, which means it's also 8.314 joules per mole times Kelvin. And in chemistry, I think you see it without the overbar, but here we're using the overbar to indicate that this is a quantity per mole. And so this is just a rewriting of the ideal gas law. Which says P times volume is equal to N times R over bar times T. Or equivalently, the same thing is P times the molar specific volume is equal to R over bar times T. That's not the form that we're going to use. So this is the more common chemistry form. But we're going to use a different form that makes it easier to look stuff up in tables. So with values that you can find in tables. So we're going to define a new gas constant, R, without the over bar, that's equal to R over bar divided by the molar mass of the gas that you're talking about. So this is universal. This is the mass per mole. And notice that that's specific to whatever gas you're looking at. And that means that this R that we're going to use as the gas constant is also specific for one gas. So if you're doing a calculation with oxygen, it's different than a calculation with nitrogen. Okay, you have to look that value up. If you make the assumption of an ideal gas, then here are the things that you know. The pressure times the specific volume is equal to R times temperature. That's going to be our form of the ideal gas law. The specific internal energy, just like it was for liquids, is only a function of temperature. The specific enthalpy is the specific internal energy plus RT. You can see that just straight from the ideal gas law, because the definition of specific enthalpy is the specific internal energy plus PV, and PV is equal to RT. Okay, so remember these two R's are not universal. And you can also simplify the calculations of CV and CP. CV is just the total derivative of the specific internal energy with respect to temperature. And CP is CV plus R. And this again is that non-universal constant R.
Yeah, so this R is just going to be in terms of kilograms as opposed to in terms of per mole.
So let's see. Yeah, I guess that's right.
Yeah, so mass of stuff per mass of
Yeah.
substance as opposed to per mole of stuff.
Mm-hmm. Yep. So let's do a problem. Okay, so let's say we have half a kilogram of air in a fixed tank, so if a problem tells you something happens in a fixed tank, there's something it's usually you're going to use. What do you know about the gas? Yeah, that's right. The volume isn't going to change. And let's say we add heat. And it goes from a temperature T1 of 20 degrees Celsius and pressure P1 of 101 times 10 to the third pascals to a pressure P2 of 202 times 10 to the third pascals. Assume that air has a molar mass of 29 kilograms per kilomole. What's the final temperature, T2? So 29 kilograms per kilomole, we can rewrite that in SI units as 29 times 10 to the minus third kilograms per mole. So let's first calculate the specific volume, because we know that it's a fixed tank. That's going to stay the same. So we have the starting pressure times the starting specific volume is equal to R times the starting temperature. So 101 times 10 to the third times V1 is equal to 8.314. That's the universal gas constant, divided by 29 times 10 to the minus third. So that's our specific gas constant, times the starting temperature of 20 degrees Celsius. So to use the ideal gas law, we need the temperature in Kelvin. So 273 plus our starting temperature of 20 Celsius is 293. Rearrange that and you get that the starting specific volume is equal to 0.832 cubic meters per kilogram. And since it's a fixed tank, that's also the final specific volume. And now that we know the final specific volume, we know the final pressure, we can just use the ideal gas law to calculate the second temperature. So at state 2, we have 202 times 10 to the third times 0.832, the specific volume, is equal to, so we have that same R again, times the final temperature. And now you can just solve for the final temperature. And you get 586.22 Kelvin. So when I was talking about the incompressible model, I finished by just giving a list of the stuff you can calculate under what conditions. So let's do that again here. So first, notice for ideal gases. Notice that you can calculate any one of pressure, specific volume, or temperature at a state given the other two. Second, you have to be careful with this because du dt changes a lot more with gases than it does with liquids, but you can calculate the change in specific internal energy as equal to CV times the change in temperature for small changes in temperature. For liquids, you can do it for much bigger changes in temperature. And third, you can calculate CV or CP given the other one. Any questions about that?
You do defined small changes. Is that just telling us the larger the change, the less accurate
Yes,
it is?
that's all. That's what it means. Yeah.
Is it range, or
No.
it's a problem?
I would say if you see a problem where it talks about 1 or 2 degrees, like say to yourself, like, why would they do a problem with such a small temperature change? And then think like, maybe this is a reasonable thing to use. You know what I mean? All right, well, I guess I'm not going to get into a new topic today, but the next thing we're going to start is, so next time, we're going to get into control volume analysis. And we're going to use 2 laws for this. The first one is conservation of mass. There was no conservation of mass when you're dealing with a fixed mass of material because there's nothing to analyze. It's just the same mass the whole time. but we're going to see some cases where it'll be useful to do a formal analysis of how much mass is coming in, how much is going out, and what that means for the change of mass inside the control volume. And then second, the one we're going to use more is we're going to use the first law for control volumes. And this gets surprisingly messy. But really the key to using it successfully is being good at recognizing what things drop out, go to zero for your specific case. You know, there are a million terms in it, but almost all of them are going to drop out in every case when you use it. And which ones drop out is different in every case. You have to like get used to just thinking through like, okay, the work coming in, is that zero? Is the potential energy change zero? Is this? And so that's what we're going to be like sort of working on after I derive that equation. Any questions?
Got one related to linear interpolation.
Yeah.
Mostly just when it comes to, when you're doing the three-step linear interpolation.
Yeah.
How we've been doing from one point X to another point X, finding that point there.
Yeah.
And that point there. Is there any difference if, for example, when we're pulling values on a table doing that three-step, there's kind of not a comparison to, points in X as opposed to points in Y? We're selecting for, our three-stage linear interpolation.
No, the order, is that what you're talking about?
Yeah,
it does not matter at all.
Okay.
Yeah.
Does it give you the same value?
It gives you the same value because it's taking four values basically and assuming it's a flat plane between them, and it's finding that value.
Okay. Yeah, mostly it was just the last linear interpolation problem. I think it was number 3, or pulling values from a table. How to go about it, because if I remember correctly, that one's 3 steps, right?
I don't remember.
Yeah, I have to look at it.